Hello everyone, it is with great pleasure I welcome you all back. Today we're going to be looking at Bernoullis equation application, and more specifically we're going to be looking at the efflux speed. So imagine we have a tank. It contains some kind of fluid, and it's open to the atmosphere on the top. And we have a hole, as you can see in the diagram, at position number 1. So let's say we're trying to calculate the velocity by which the particles are leaving, okay? So in other words, the efflux speed of the fluid particles. So what would we do? For that, we would actually use Bernoulli's equation. So let's go to a sketchbook and let's see how to actually do this. Okay, so as you recall from the previous lesson, so we have Bernoulli's equation simply is pressure 1 plus 1/2 rho V1 squared plus m times g times h1. Okay, of course that's going to be rho gh equals p2 plus 1/2 rho v2 squared plus rho gh2. Okay, so we have to, at this point, manipulate this equation in order to be able to calculate the speed by which the particles are leaving the second hole. So here is, of course, our tank. Like this, we have a hole at the bottom, and water is coming out this way. Here we go. So, first of all, how are we going to do this? Let's check this out. Look on top. It's open, obviously, to the atmosphere. So the pressure for that obviously is going to be 1 times 10 to the 5th. And look at the hole. The hole is very, very, very close to the top. So we say that the pressures are pretty much the same, and we can actually cancel them out. So the two pressures that are being applied on either hole right over here. So for example, this is going to be number 1 right up here, and this is going to be number 2. We say that it's the same. Now let's look at the velocities. Look at this top velocity over here. This top velocity by which the particles are going to start to descend is going to be a lot slower by which they exit this side hole over here. So we say that this is going to be close to 0. It's not exactly 0, but we say it's pretty close to 0. Now, let's look at the height. Over here we have the fluid height of 1, and over here we have the fluid height of 2. So we can take it in reference of this height right here. So we say that the second hole has a height of 0, and the first hole has a certain height which we call h1. So because we consider this height to be 0, we can also cancel this term out and say that simply that it's 0. So let's look at our equation now. What does it become? Our equation now becomes rho times g times h1 equals 1/2 rho v2 squared. So now it becomes an easy solve. As you can see, a lot of the terms have been canceled, so we can solve now for v squared. So what do? We multiply both sides by 2, as you can see right here. This cancels out. And also, we have density on either side. So what can we do for this one, guys? We can also cancel it out. So our equations now, I'm just going to flip them quickly, and we see that it's going to be velocity 2 squared. So the velocity by which it's leaving over here equals to 2 times g times h1. And now, of course, we take the square root on either side, and we clearly see that v2 equals the square root of 2 times g times h1. And that's how we use this equation in order to solve the velocity by which the particles are being ejected over here. So you're going to use this, and you're going to use this equation right here, and you're going to solve all the problems that are available to you on Google Classroom. Thank you so much. See you in class.